Did you know that black holes can photobomb stars? I'm Dr. Laura Driessen, and I'm a radio astronomer at the University of Sydney, and I search for radio stars. But before we talk about stars, we have to talk a little bit about light. Does anybody know a different kind of light other than the light that we can see with our eyes? I can give you a hint. There's a kind that burns us. UV, yes. What about when you break a bone? What kind of light might we use? X-rays. There's also gamma rays, which turned what's his name into the Hulk. If you know your Marvel lore. But if we go the other way, we can go down to different kinds of light. Infrared, for example, like infrared night vision goggles. Microwaves are literally the kind of light that you use to heat up your food in your microwave oven. And then the lowest frequency of light is radio light. So those are waves of light that can be as big as 21 centimeters, which is pretty big. You can hold that in your hands, up to meters in length. And that's the kind of light that I search for star. Now, most stars do emit some radio light. For example, our sun is a little bit of a radio star, but luckily it's pretty quiet, which is good for us because otherwise we would be dead if the sun was a bit more active. But I'm looking for stars that emit lots and lots of radio light. But how do we find those? It's actually a lot harder than you think, because you might be thinking, I can look up at the night sky and find hundreds of stars. You can stop your research, it's all good. We're good to go. But when I look up at the night sky with my telescope, I see a whole lot of dots, and almost every single one of those dots is a black hole in a distant galaxy. So if I take a picture of the sky in the opticals, and I see a whole lot of stars, so this is the kind of light that you see with your eyes, and then I take a picture of the same patch of sky with radio light, I also see a whole lot of dots. And then I might go, oh, let's see if any of those dots line up. Maybe a star is a radio star, and I go, whoa, we did it. Except space is not 2D, it's 3D. And when we take a picture, we can't see that third dimension. So almost every single time when I think I found a radio star, it's actually a distant black hole behind that radio star. So it looks like the radio light is coming from the star, but it's actually coming from way behind it. So that's how black holes can photobomb stars. And my research is to try and find ways where we can actually work out when the radio light is coming from the star itself and not from some distant black hole behind it.
So how do you get that depth perception?
It's really tricky. So we can do that with stars, as long as they're close enough by. And we use something called parallax. Basically, the Earth goes around the sun, and we use that distance when we're on one side to the other to measure the angle to the star, and then we can use our good friend trigonometry to get the distance, because we know the distance between those 2 points and we know the angle, and then we can work out the distance. But that sort of breaks when you get too far away. Basically, the angle gets so small that you can no longer use it. So distance is really, really tricky. We can also use redshift. So as things move further away, that light becomes more and more red, and we can use that to work out the distance to things. But that sort of then only works when things are far enough away. So there is a lot of stuff in space that we sort of never know the distance to. So we can't really use distance to work this out, because in the radio, getting distance is almost impossible, unless you do have that redshift. But you can't do that in the radio. We actually need the optical light to get redshift. So you have to have some other type of light in order to get distance. So usually we don't know the distance, and that's what makes it extra hard. We tell the difference in other ways. So you know about polarized light, like our sunglasses have polarized light. So light can be polarized, so the wave is basically traveling sort of one direction or another direction. Stars and something called pulsars are the only things in the universe almost that have something called circular polarization. So what that means is light actually has both components of polarization, so it looks almost like a corkscrew. So if we take a picture of just circularly polarized light, then suddenly almost everything in this whole picture would disappear except 1 or 2 dots. And those ones we can tell are either a pulsar or a star. So that really narrows things down from millions to really only a couple of hundred things in the whole sky. We can also use motion. So if you imagine a car drives right past in front of your feet at 60 k's an hour, it looks like it's moving very fast. But a boat on the horizon moving at 60 k's an hour barely moves at all. Stars are all in our Milky Way, the ones that I'm talking about anyway. They're other stars, but the ones I'm talking about. So we see them all moving around. But galaxies are so far away that on human timescales we'll never see them move, even though they are moving. So that's one of the other ways that we can actually work out. We can see something moving. Problem is it takes years. The last time I did that, I had to use data from 30 years ago and compare it to today to see if anything moved, and I'm not really that keen to wait another 30 years. So I have to think of other ways to find the difference. We can also use some of the other properties. Some of these stars, if they're also X-ray stars, so if they're also emitting X-ray light, that sort of links up to the radio physically. So that gives us a bit of an indication that maybe it is the star if you see it on the radios. There are a few ways, but they're all kind of sideways. We can't just come at the problem head on.